The Standard Model. In 1932, the atom was visualized as having a nucleus containing neutrons and protons deep within an atom and surrounded by electrons. Illustrated to the left is a helium atom with 2 protons and 2 neutrons shown in red and purple. The width of the nucleus is 1 × 10⁻⁷ nanometers. The diagram shows a magnified view of the nucleus. It fits within the darker circle. What is the significance of the dark circle surrounded by the lighter shades of gray? The cloud represents possible positions of the 2 electrons that are part of the atom. The darker the shade means that it's more probable that the electrons are found within that shape. The other particle known in 1932 was not part of the atom, has no mass, and is responsible for electromagnetic phenomena such as electricity, magnetism, and light, the photon. Physicists were explaining nature's behavior in 1932 with just the following particles: photon, electron, proton, and neutron. Then, in rapid succession, and for the rest of the 20th century, more particles were discovered: positron, mu lepton, pi meson, k meson, antiproton, electron antineutrino, muon neutrino, W and Z bosons, gluon, top quark, Higgs boson, and many, many more. But before we get into that, let's examine the forces that were known to act in the universe. There are 4 fundamental forces in the universe, and all were known in 1932: electromagnetic, strong nuclear, weak nuclear, and gravitation. And these forces are ordered from largest to smallest. Does it surprise you that gravitation is the weakest force? Think about the electric charge and force chapter, where it was shown that a plastic ruler rubbed with fur could lift bits of paper. That small electric force was able to move the paper in opposition to the gravitational field provided by the entire planet Earth. The electromagnetic force. The forces of magnetism and electricity were shown to be the same force, and mediated by the same particle. In this case, photons are exchanged by atoms and cause the electromagnetic force. Many physicists worked on this integration, but the seminal work was done by James Clerk Maxwell and Michael Faraday, finishing in 1873. The word mediate is one of those times that physicists take a word that can mean many things in non-technical conversation, but has a very specific and different meaning in physics. Mediation explains the action of the fundamental forces as the exchange of special particles between atoms and molecules. The strong nuclear force is the force that binds neutrons and protons together, postulated in 1932 when James Chadwick discovered the neutron. This force is mediated by the gluon. The weak nuclear force explains beta decay, where a neutron in the nucleus decays into a proton and emits an electron and an antineutrino. Theorized first by Enrico Fermi in 1933, this force is mediated by the W and Z bosons. We will study beta decay in the next unit. Finally, gravitation describes the attraction that masses have for each other and was developed by Isaac Newton and then revised by Albert Einstein with the theory of general relativity in 1915. This force is mediated by a proposed but not observed graviton. The forces are organized here in order of decreasing strength. The difference in relative strength between the strong nuclear force and gravity is tremendous. See relative strength? If gravity is 1, has a strength of 1, the strong nuclear force has a strength of 10 to the 38th power. The ranges over which these forces act is also different. The ranges of the electromagnetic and gravitational forces are infinite. However, the 2 nuclear forces are very short ranges. They only act over the distances inside an atom. A fundamental particle, also known as an elementary particle, is a particle that is not composed of any smaller particles. Electrons and photons are both fundamental particles. Nucleons, which is another word for protons and neutrons, are not fundamental particles. They have underlying structures. Each nucleon is actually made up of 3 fundamental particles called quarks. The farther quarks get away from each other, the more strongly they are attracted, unlike the forces of gravity and electromagnetism, but analogous to the behavior of the spring force. Interesting how a fundamental force can be thought of as a spring. Here is a table showing fundamental particles that have been found. Included are photons, electrons, neutrinos, and quarks. There are 6 types of quarks: up, down, strange, charm, top, and bottom. Each type of quark has different properties, including charge. Up quarks have a charge of 2/3 e, a positive charge, and down quarks have a charge of negative 1/3 e. You may be thinking, I thought there were no smaller charges than e, the elementary charge. How can you have fractions of e? However, quarks are never found alone. A neutron, shown here, is composed of 1 up quark and 2 down quarks, adding up to 0 charge, 2/3 minus 1/3 minus 1/3. A proton is 2 up quarks and 1 down quark, adding up to a charge of 1, positive 1. So we have 2/3 plus 2/3 minus 1/3 equals 1 e. In the late 1960s, work was begun on the Standard Model, which is the current theory uniting the electromagnetic, strong nuclear, and weak nuclear forces, and categorizing the multitude of elementary particles that have been discovered. The electromagnetic, strong nuclear, and weak nuclear force theories are all compatible with special relativity and quantum mechanics. But to this date, the gravitational force has not been found to be compatible with quantum mechanics and is not part of the Standard Model. The particles also have antiparticles. Antiparticles are identical to the particle, just with an opposite charge. For example, the positron has a positive charge and is the antiparticle of the electron. The antiproton has the same mass as a proton, but has a negative charge. When a particle and its antiparticle come close together, they annihilate and release a photon with energy equal to mc². Antiparticles are represented by a horizontal bar over their letter, or by a different sign for the charge. A positron is normally shown as E+. An antiproton is shown as P with a bar on top.